To compute the directional derivative for a function, we can use the following to evaluate the directional derivative of a function in the direction of u at x0, y0. We have a formal definition for computing this derivative with limits. But in practice, we can use the following formula to make this computation. So to compute the directional derivative, you're going to take the partial derivative of f with respect to x, evaluated at x0, y0. Multiply that times a. Again, that a is coming from this vector u, where u is equal to the vector a comma b. And add the partial derivative of f with respect to y at x0, y0 times b. And again, that b is coming from the y coordinate of our vector. So again, given a unit vector a comma b, you can compute the partial derivative by evaluating this expression. If your unit vector is given by an angle theta, recall that the unit vector would have coordinates cosine theta for the x coordinate and sine theta for the y coordinate. So the directional derivative in the direction of u of f at x0, y0 would be the partial derivative of f with respect to x at x0, y0 times cosine of theta. Again, that would be our like our a within our unit vector, plus the partial derivative of f with respect to y at x0, y0 times sine of theta, where again the sine of theta would be the y coordinate vector of our unit vector. So let's see this in action, starting with this extra problem. Let f of xy be equal to e to the xy, and let's compute the directional derivative of your function f of xy at the point 1, 2 in the direction of v equal to, let's say, 4, 5. One thing to note is that this v is not a unit vector. So the first thing I should do is rewrite this vector to be a unit vector by using the technique that we covered above. So again, if you want to create a unit vector from v, you're going to take v and divide by its length. So we'll have 4, 5 divided by the length of v, and that's computed by the square root of 4 squared plus 5 squared. That's 25 for this value, that's 16 for that value, so that will be 41. And we can take that radical 41 and apply it to the first element and the second element, and this guy would be your unit vector to use in the computation for the directional derivative. All right. So now, if I want to compute the directional derivative of this function in the direction of u at the point 1, 2, I have to take the partial derivative of this function with respect to x, evaluated at 1, 2, multiply that times my a of 4 over rad 41, add the partial derivative of f with respect to y at 1, 2, multiply times my b of 5 over rad 41. To compute the partial derivatives of f with respect to x and the partial derivative of f with respect to y, we take a look at our function e to the xy. For the partial derivative of f with respect to x, we're going to consider the y value to be constant, and this partial derivative of this exponential is going to have that same exponential in it. And then the partial derivative of xy with respect to x is simply going to be y. Similarly, the partial derivative of f with respect to y is going to have that same e to the xy in it, and the partial derivative of xy with respect to y is going to be x. Evaluating these expressions at 1, 2 for our partial derivative of f with respect to x at 1, 2, that will give us 2e to the 2. We're multiplying that by 4 over rad 41 plus the partial derivative of f with respect to y at 1, 2 will give us 1 e to the 2, and we're multiplying that times 5 over rad 41. So this right here is a real number, and this represents the slope that we will be experiencing if we would be pointing in this direction and walking along the surface of this function e to the xy. So again, for this problem, we were given a vector and we computed the directional derivative along that vector. Compare this to what we have in example number 2. In example number 2, we have a function f of xy given as x cubed minus 3xy plus 4y squared. And we're asked to compute the directional derivative of f of xy at the point 1, 2 in the direction of the unit vector generated by theta equals to pi over 6. So we're given an angle theta, and on the xy plane we're going to go pi over 6 units out and use that to generate a unit vector in that direction. And again, this unit vector will have coordinates cosine of theta, sine of theta. So the cosine of pi over 6, sine of pi over 6. The cosine of pi over 6, that's rad 3 over 2. The sine of pi over 6 is 1/2. Just for reference, we'll also need the partial derivative, so let's go ahead and compute those out. Before we compute the directional derivative, the partial derivative of f with respect to x, that's simply going to be 3x squared minus 3y. If we're evaluating this guy at the point 1, 2, that will be 1 squared minus 3 times 2. So that's 3 minus 6, negative 3. Taking the partial derivative of f with respect to y, we would have negative 3x plus 8y. And evaluating this partial derivative at 1, 2, we would have negative 3 times 1 plus 8 times 2. So that's 16 minus 3, so that's 13. So our directional derivative of our function in the direction of u at the point 1 comma 2 is equal to the partial derivative of f with respect to x at 1 comma 2 times your a, or rather times your cosine of theta, plus the partial derivative of f with respect to y at 1 comma 2 times the sine of theta. And we have values for all four of these guys here. So this would give you -3 times the cosine of theta of radical 3 over 2 plus 13 times 1/2. Cleaning this up, you got -3 rad 3 over 2 plus 13 over 2. So again, this is a real number. This is giving you a sense of whether you're going up or down and how much you're going up or down when you traverse the surface of this curve in the direction of pi over 6 units.